So hello everyone, my name is Marin Kac and I'm a PhD student at the Faculty of Electrical Engineering and Computing at the University of Zagreb. I'm going to present my research on the topic of end-to-end automatic road safety assessment. I'm going to cover road safety and IRAP attributes. I'm going to talk about the dataset that we've acquired. I'll follow it up by describing our first automatic approach, which is a vision-based model, and that will be followed with an analysis of attributes which inspired our improved model. Then at the end, we're just going to show our results and conclude the presentation. Now, with 1.35 million deaths per year, road traffic accidents are a significant public health problem. The International Road Assessment Program was founded with the goal of preventing and reducing fatalities through safer roads. Now, even the internationally accepted Safe System approach identifies 5 key components for improving traffic safety, and one of those is safe roads. And lastly, even the UN defined road safety as one of its sustainable development goals for this decade. The IRAP star rating is a robust measure of road safety, where each section of the road network can be assigned a value from 1 to 5 stars. And the rating is calculated using a formula which takes in 52 different road infrastructure attributes. It has been shown that traffic-related fatalities drop exponentially as the star rating improves. For example, in New Zealand, there was a 2-star road section with a previous record of accidents, and using the star rating as guidance, infrastructure attributes were improved to increase the rating to 4 stars, and since then there have been no fatal crashes or injuries. There are 52 road safety attributes, and each one of them can have multiple categories, so we can think of each attribute as a multi-class classification problem. The value of each attribute has to be determined for each road segment. As an example, one attribute is road delineation, which is concerned with the adequacy of lines and markings on a particular road segment, and it has 2 classes called adequate and poor. Currently, IRAP attributes are coded manually for each segment by human experts. We want to automate that process, and so we formulate the problem as video or image classification. We align video frames with road segments and then classify the segments based on that input. Our main dataset that was acquired throughout the country of Bosnia and Herzegovina consists of georeferenced front camera videos of about 2,300 kilometers of various kinds of roads, where all segments have been annotated with all attributes by trained experts. One very important issue that arises with this and many other real-world datasets is a severe class imbalance, which is present in a majority of attributes. This is a very important issue that we will refer back to multiple times. Our first approach was a vision-based model, which classifies a segment by taking multiple frames that represent it and processes them with a convolutional neural network, which works in a multitask manner and tries to predict the values of all the attributes at once. The exact frames that the model takes for a given segment t are the middle frames of segments t, t-1, and t-4, which gives the model more context and resilience to occlusions. The convolutional neural network consists of 2 main parts. The bulk of the network is a shared backbone which acts as a feature extractor and outputs a vector which is then passed to individual attribute-specific classifiers. The shared part of the network consists of a ResNet-18 encoder, which was pre-trained for the task of semantic segmentation on the challenging Vistas dataset. The feature maps output by the encoder are pulled by the spatial period pooling module. In the attribute-specific part of the network, that part consists of attention pooling, which has a learned query vector for each attribute, and the result is then concatenated with the result of the SPP module, and that vector is given as input to the attribute-specific classifiers. All classifier heads are trained with some variant of the cross-entropy loss, and finally the total loss is calculated as a mean of all individual per attribute losses. To handle multiple frames, the encoder, the pooling modules are all applied to all frames independently, and the resulting 3 vectors are concatenated and fed to fully connected classifiers. We use weighted cross-entropy loss to address class imbalance during training, where the idea is to give more weight to rare classes to prevent the model from ignoring them. Since we're doing multitask learning and averaging many individual losses, it is important that the magnitude of each individual loss is roughly maintained. Thus, it is crucial to use this specific formulation when averaging losses of examples in a batch, where the denominator contains the sum of weights of all examples in the batch. There are different schemes of assigning weights to classes, and the common approach is to have the class weight be inversely proportional to the frequency of the class in the dataset. For rare classes, this kind of weighted loss essentially gives a larger penalty to false negatives, and it sacrifices precision to gain recall, meaning that the class is not ignored. If a certain rare class gets a high recall during training, it would be a good idea to decrease the weight on that class going forward, as otherwise we would be wasting precision. So an improved weighting scheme is to dynamically recalculate class weights after each epoch and decrease weights for classes that have higher current recall. The conclusion of experiments on this vision-based model was that the most important aspects were Vista's pre-training of the encoder, using multiple frames, and using the weighted cross-entropy losses. Regarding evaluation, to address class imbalance, we use the macro F1 measure, which averages F1 scores for each class, and so all classes contribute to the score equally regardless of their frequency. The results of experiments will be displayed at the end of the presentation. Now, since each road section is a long sequence of consecutive segments, after we developed our vision model, we thought about analyzing the temporal behavior of attributes. Each attribute can have a different temporal behavior patterns and specific annotation conventions given by the IREP standard. We wanted to compare such temporal behavior between ground truth, correct labels of segments, and the prediction that our model gives. And we wanted to observe eventual discrepancies between those two to gain further insight. For example, certain attributes have a notion of a default negative class, which denotes no occurrence of an infrastructure element, while all other classes are treated as positive classes or occurrences. The positive classes, by convention, must be annotated in only one segment per occurrence, so there can never be a case with multiple consecutive segments of a positive class for one occurrence. One example is the attribute intersection type, where the negative class is no intersection, and then when an intersection occurs, only the one closest segment to the intersection must be annotated. The intersection in reality might cover multiple consecutive segments, and the frames of those segments might be quite similar in that they contain all the discriminative visual features that are needed to recognize the intersection, yet only the one segment is annotated as positive. We call such attributes single peak attributes. So for vision-based models with very local temporal context, it might be difficult to decide which exact segment should be annotated as positive with such attributes. In contrast with single peak attributes, there are attributes which are by nature quite smooth, in the sense that they rarely change classes. These usually describe certain areas or environments or infrastructure elements which don't change often. These have a lot of temporal redundancy, and we call them smooth attributes. Now, aside from these two types, there can be other more complex temporal patterns that can occur with each particular attribute. After this conceptual analysis, we wanted to empirically compare consecutive ground truth labels and predictions. We do that by analyzing classes of all possible pairs of successive segments for each attribute. So for each attribute, we want to build a co-occurrence matrix in the following way. For each pair of segments t-1 and t, we'll look at both of their classes and increase the corresponding element in the co-occurrence matrix. If a certain segment was in class Ci and that went to Cj, the element ij is incremented. So we build such a matrix for each attribute, but we actually build two such matrices, one for the correct ground truth labels and the other for the predictions of our trained model. The idea is then to try to analyze discrepancies between these two matrices for each attribute. Now, before we construct these matrices, let us think about these matrices for those two specific types of attributes that we described. So for single peak attributes, the ground truth matrix would only contain non-zero values in the row and column which correspond to the negative class, since the positive class is only ever annotated once per occurrence. So if the prediction matrix has values that are not on this row and column, that will be an indication that our model has failed to capture this annotation convention of such an attribute. On the other hand, for smooth attributes, which usually change very rarely, we expect the ground truth matrix to have very high values on the diagonal and very low values outside the diagonal, because all of those elements on the diagonal denote pairs of segments where the class hasn't changed. If the prediction matrix has smaller elements on the diagonal and is more dissipated, meaning it has larger values outside the diagonal, that might indicate to us that the model has failed to grasp the temporal context of a smooth attribute. So now we construct these matrices and we give a few examples here. So for the attribute number of lanes, which is by nature quite smooth, the ground truth matrix is on the right, and we can see it has large values on the diagonal and very low values off the diagonal. The prediction matrix, however, has significantly larger values outside the diagonal than the ground truth matrix. There's a similar case with the attribute Roadworks, which is also a smooth kind of attribute. On the other hand, looking at a single peak attribute like the intersection type, we see that the ground truth matrix only has non-zero elements in the row and the column of the negative class. Again, the prediction matrix differs in this respect, since it does have elements outside those row and column. Mostly, these elements outside that row and column are focused on the diagonal, which means that these are occurrences where consecutive segments were classified in the same positive class. So for instance, for the three-legged intersection, the model saw the visual appearance of a three-legged intersection in multiple consecutive segments and decided to classify them all in that class, which isn't that incorrect, but it does not adhere to the annotation convention of the single peak attribute. And so we conclude that the model didn't capture the temporal behavior of this specific attribute. And inspired by this analysis, we decided to improve our approach by using a larger temporal context and using a sequential model. More precisely, we used long short-term memory network, which has been shown in various tasks to be able to learn specific sequential rules and patterns. We use our vision-based model, denoted here as the CNN classifier still, to process each segment and take the logit outputs and give those outputs as inputs to the LSTM. And the LSTM covers a much larger temporal context, which consists of 10 segments before and 10 segments after the current segment. Now, since the inputs are very low dimensional, the whole model is very lightweight and is quickly trained and evaluated. Thus, each attribute can have its own bidirectional LSTM, which learns its specific temporal behavior patterns. So for the results, we train and evaluate our model on our Bosnia and Herzegovina dataset. First, these are the macro F1 scores averaged over all attributes for different variants of the approach. We see the impact of the following modifications: using Vista's pre-training, using the inverse frequency weighted loss, using the recall-based loss, and finally the contribution of using the sequential model that covers a larger context. When looking at per attribute results, some attributes have the macro F1 in the high 90s, and these are ready for industrial deployment, while there are some attributes that are far more complex and essentially very hard, like roadside severity, for example. There are quite a lot of attributes which do have high accuracies but low macro F1 scores. These attributes have severe class imbalances usually, which means that the model doesn't learn to capture those very rare classes very well. So for accuracy, that doesn't matter, so it can still be high, but macro F1 captures that phenomenon, and this signifies the necessity of using more complex, strict metrics. We visualize the saliency of maps of different attributes on some examples, and in the upper left corner you can see the attribute sidewalk on the passenger side and see that the model focuses on the part of the image where there is a sidewalk. In the upper right image for road delineation, the model focuses on the surface of the road to detect the quality of markings. In the lower left for divided carriageway, the model looks at the physical separator of the two directions of travel. And in the lower right image, the model focused on the pedestrian crossing, which is located on the side road. We wanted to test our model on a publicly available dataset and compare it to other competing approaches. Since there's no such dataset for IRAP attributes, the closest that we found was the Honda Scenes dataset for road scene classification. Some of the tasks are quite similar to IRAP attributes, and it also has temporal annotations, in the sense that each of the subtasks in the road place task are annotated with classes called approaching, entering, and passing. So a model which can not only visually detect these elements, but can also capture temporal patterns should be beneficial here. So here are the results of two previous approaches, compared with two variants of our model. Our first variant is just a vision-based model, and the second is our improved LSTM-based model. Our models outperform the competing approaches. In conclusion, there are various paradigms that people use to tackle road safety assessment. Some of these approaches are based on analyzing statistics and historical records of accidents. These approaches might yield high variance predictions when extrapolated across the whole network, since accidents are very rare. Also, such a paradigm is fundamentally reactive in nature, in the sense that accidents need to occur for the road to be identified as dangerous. A lot of the other approaches which assess road infrastructure, they require hard-to-obtain data such as LiDAR point clouds or images from calibrated stereo cameras or other data sources. Furthermore, a lot of the approaches are not really that general and don't tackle IRAP attributes directly. They use existing models to detect general objects and then use some handcrafted rules to connect those to IRAP attributes. And these systems might be quite brittle and hard to adapt to different attribute sets, and sometimes only tackle small subsets of attributes. On the other hand, our approach was, from the beginning, was designed to be very general and adaptable to different road safety standards easily, and it is proactive in nature in the sense that it assesses road infrastructure by itself without basing its predictions on historical data. The input data required can be obtained by inexpensive cameras, and the model itself is very lightweight so that it could be run even in real time on device. And now, when we take into account the fact that road infrastructure isn't static and that it changes over time through improvements or deterioration or civil engineering activities, and then we see that inexpensive approaches, which can refresh data often, or even real-time approaches, are beneficial. Just as an example, specifically for real-time inference, our model should be slightly modified to satisfy what is known as causal formulation, where the model doesn't see the future segments. We briefly tried such modifications and they were still able to maintain quite a high level of performance. This brings me to the end of my presentation, and I want to thank you all for your attention.